logo places. At first, I thought it's a logo for a coffee shop, sovereignty. They told me that no, this is the logo for the MCU. They asked what does it mean. It can mean many things. At universal level, that means that the starter will want to tackle challenging problem in science. So this reminded me my first stay in KTH in 2008. So I come to the campus, there's a big logo. This is the logo of KTH. There's a big logo above that. And then in between, it has 2 words or 3 words. So that was the first English word I learned. That will be translated immediately. It means science and art. This is the key of the university. I was surprised, but the same way, because the KTH is known as engineering school. The science is really a small part, teeny tiny part of the school, and we don't do any art. So I make a joke of this logo every time I have a visitor. But eventually came up with an explanation. So the art here means that we want to do science that gives you a simple spectrum, or the science that can be applied to technology in a simple way. And also when I came to the group, I proposed many things to study, especially for computer coming at that time to get to Sweden. They said, no, we don't do the complex stuff. We want to do something simple that can be measured. So this is something that I learned, and something that I have in mind, so I've been giving it to me. So what I'm telling you today is something that's very, very simple. It's based on textbook. And manual calculation can be done by hand. Actually, I was doing manual mostly at the back end. Until recent, we get a symbolic calculation. And after 10 years, basically, slow progress, all of a sudden, it seems like there is independent evidence for that. Before I was working on that mostly as a toy model, even where it never come true, but it did come true. So I divided my talk into 4 parts, mostly focused on the basics. I will start by telling you what is seniority, just remind you of textbook definition of seniority, and why it's still relevant today, and where it is partially conserved, and how that can be measured. That is my plan. I start by reminding you. Yeah, I can. It's okay. I can use this one instead. Yeah. I start by reminding you that very often in nuclear physics we start with the independent particle model that was proposed in 1949. Actually, in that model, Mayer implicitly applied this concept of seniority, which was proposed by Raka in 1943, respect, where he assumed that if I have particles from it, 2 electrons or 2 nucleus that couple to spin 0, I will call this state seniority 0, so my 2 particle pair. And if I have a single particle, not paired to 0, I will call this system seniority 1. You can define different systems, so on and so forth. So in the independent particle model, and Mayer simply assume that okay, my even nuclei, they all have spin 0 in ground state. That means all even nuclei will have seniority 0, and all the particle or all the mass nuclei will have seniority 1. This will have 1 particle in the pair. So with that, you can explain the Lorentz state for the even as well as for the body. Okay, and there are many ways to define the mean field, as we are doing here by DFT or by shell model, I mean by ab initio theory, or if you do as we do back in Stockholm, like you use a simple suction, which also works equally fine in some cases. And the seniority is defined not in the Coulomb space, but in the configuration space. It's always defined by a single particle state first. Okay. So why it is relevant? So when this kind of concept was introduced by Raka in quantum physics, it was not so interesting because in quantum physics, the electrons they are repulsive. But in the nucleus, when you have the two-part couple to spin zero, it turns out like I took the illustration from a paper which I don't remember now for me. So I'm going to put the reference here. But things out like you can easily check, especially if you have effective detection. But if you have two parts coupled to spin zero, you have larger overlap at short distance. So this gives out a larger fraction for the spin zero state. And if you have a state with different spin, for 2, 4, and 6 in this case, the interaction is typically smaller. So this is something that you can see from the effective interactions. You look at the shell model. Quite often, if you look at T for one interaction, the J for zero part is strongly attractive. And meanwhile, the other spins typically around 0. Okay. So quite often, it is fair enough just to have a parent Hamiltonian with only J for zero terms, or less set to 0, which works for the conditions if you want to create a BCS. So this is just a comparison for the solution. So I start with a field where I don't have any interaction. If you want to be BCS, so you can do any kind of apparent Hamiltonian as a computer system. And if you look at the book of Mortensen, quite often is it is good enough to represent it as a constant or scaled constant. And the shell model will go open like this. We have both the T for 0 state and the others, which is slightly different energy. This can be taken from the little potential, you can take the potential with those works. A few remarks here. So this part is always strongly attractive, always. And the others are close to 0, as I said. And if you apply this kind of Hamiltonian to seniority, you will see that your seniority is preserved automatically for the shells. It is smaller than the same. It's just due to geometry, nothing to do with actions. Every state is uniquely defined by seniority and spin within the mix. And if your Hamiltonian contains only parent, this seniority is preserved. Basically, the environment. But if you have a releasing case, if you have open shell, your neutron proton interaction will create seniority to a large extent, especially T for 0 from neutron interaction is really. That's why we start to have this kind of quote conditions. So primarily when we see what the seniority is still mostly relevant for supplementary nuclei. Okay. But if you are going very far away from A equals A and opening fundamental, seniority is still a very good approximation, but not around A equals A. See to work. Yeah, good. There has been many applications for seniority. Maybe the most known one, or the textbook example, is the explanation of the binding energy difference. Okay. So if I have a system in a single shell, for example, F7 in this case, you can get an analytical solution of the binding energy. Okay. So in this case, I will assume that it has 40 as the core. That all dynamics, all the ground state properties are governed by the coupling to organic particles in a single reaction. Okay, and then your energy will be simply expressed in this form. So it will be this contribution from a single part, this contribution to core, this contribution from single part energy, this contribution from the and this contribution from the energy. So this ground cage is the number of pairs I have in the system. If I have n equal 2, that means I have 1 pair. If I have n equal 3, I can still have 1 pair. If I have n equal 4, I have 2 pairs. Okay. And you see that if you are going from 1 pair to 2 pairs, in the middle, you lose energy. You don't need it. So that's why you see this kind of step in the separation energy. So even once the more bound than the old, due to the extras, having energy, this also intensity. And this is for the protons of energy isotopes. And here I have neutrons in the F7 proteins. So this goes very nicely. How does it work in reality? So if I start with a part pair like this, up to spin 0, it is trivial and it's unique. Actually, you can also define 2-part state with other spin as unique states. Very easy, straightforward. And recall to go from 2 particle to 9. That's for that. Of course, you can go with BCS, anyways, or if you go with seniority, that means I will start with one pair, like this. Just start to edge the pairs on top of that. Okay, so if I have n particles, that means I can reach a minus 2 pairs, most even system. And for the ground state, I assume that this is seniority 0, that means all the pairs are coupled to 0. So this will be my ground state function. Okay, actually, it turns out that for a single J shell, this is basically the same as BCS. You know, you can care about the same. But if I have, I'm not going beyond the ground state, so if I have a cycle state, I assume that if one pair can be broken, I come up with seniority 2 state, it will function like this. So it's n minus 2 divided by 2 pairs, and extra pair the coupled to different scale. So here I have a system such that many particles in the system are mostly coupled to 0 and 1 pair, similar to the 2 quasi particles. Okay, so with this starting point, you can get the energy for the different stage. So this is the energy for the ground state, for the deep state of the ground stage, and the even and okay. The reason I write it in this way is so that there is a contribution from the parent to the monochrome infection. There is a linear contribution. Also, there is a contribution from the parent at 2 particle level. That means if you have many more pairs, it just add up. This is negative, and this is positive, and this is positive. And here you give that if I have all the particle, my system lose energy for certain levels of energy. Meanwhile, if you have more pairs, my system also lose energy, means we have less freedom to develop parent. So this is once already under a single particle. Okay. And the more can be different. Or if I'm going from 1 pair to 2 pairs, or if I'm simply going from 1 pair to 3 particles, it seems trivial, but still can be some symmetry you should bear in mind. For example, if I have 3 particles in D7 half, okay, I start with a pair, 0 pair, and couple to my last order particle. So this can give me a speed of 7.5, 0 stage. Okay, as we learned next week. But I always thought about the fact that if I start with a pair with a large spins, together coupled to spins maximum 6. And this pair coupled to my last order particle. This looks very different from before. Ionistically, actually very different. This is a pair state talking about parallelism is kind of a one stage. Actually, they are exactly the same. This is due to the fact that for spin 7.5 and lower, there's only one such stage. So it doesn't matter if you start with spin 0, spin 2, spin 4, spin 6, you all come up and end up with the same state, exactly the same stage. But if you go to the spin 9.5, it will not be the case anymore. Okay, with this, you will come up with spin 1, and with this, you will end up with this 3 stage. Okay, so this is something dramatic, that kind of dramatic influence your system. Is this something special? Everything below everything is 7.5 million. That's also the reason that why seniority is just preserved, which is below 7.5 or even. Okay, this actually has a consequence. I can come back to it later. This isn't into my life. This is the only chance in my life I can cover this because it's interesting. She made this blog for me many years ago. I'm sure that it has a consequence. And if you have this subatomic with a carbon and you get this energy, you will be able to predict the spectrum. This is how the spectrum looks like. I took just one example from this review paper. If I have, I brought everything right to the ground stage. Okay, so we have an even system, we have 0 with 0, if I have all system, I was symmetry 1. If I have one pair broken, I have symmetry 2. So 3 is 4 and 5 students. Maximum is 5. So, okay. So if you have a pair Hamiltonian, it's your spectrum in that way. Of course, it's not realistic, since you don't take into account the amount of very still keep stable to the speed. But if you only direct the ground state and all that, so then you do BFT. And but part of the one bound prefer shell model, you can consider the fact that this state is slightly different. Okay. Then this is what you end up. Okay. So this is some comparison between the environment and some simple calculation, single shell. And the volume 22, we have 2 protons in the Gina subshell. So this is environment data, ground state 2, 4, 6, and 8. And this is what you can get in single shell calculation. What is remarkable is that you see that all this group, this group, is the same. This is due to the fact that in all these systems, you have only one pair that can be broken. So all the rest are just counters. Okay. So that's why this is the ground state with scenario 0. There's 3 groups with scenario 2. It should give exactly the same property, same energy, and the same heat transitions with a proper scaling to the finite number difference. But this group I call scenario 2. And here they come to the higher spins, of course. 4, since we have enough room in the scenario 2 to develop the higher spin, here we have 4 particles. Okay, that's why we get this 10 and 12. Yeah, this is basically what you can get. This is one example for the protons in the D9. I think I have one example. Yeah, this is for the protons in the H11 half. This was known quite long ago already. And if all the particles in H11 half, this is relatively nearly the same. Just due to the fact that all these systems are only defined as one pair. I have a complex system with 150 particles. There will be 2 active. Okay. I think I have one more. Now, this is the light, which is more difficult to measure, but I saw this paper in 2012. This led to 2 neutrons in H9 half. And this is 212 with 4 particles and 6 particles and many. Yeah. See that this is the ground system on 0 and scenario 2 and it's more than just okay. They look nearly the same. Okay, so they can be integrated based on symmetry model in the similar way. Okay. So that's not the end of the story. Another very important application of seniority is that it explains you also the transition properties, in particular so-called seniority isomer. This is due to the fact that this is pretty complex, but it's a transition strength of the transition matrix element. This is my initial state, this is my final state, and this is my particle number, this is my seniority number, whatever. This is really details. The key is that the transition strength is proportional to the degeneracy minus the particle number divided by the degeneracy minus the seniority number. And you can focus on it here. And just tell me that at medium shell, this number goes to 0. So this is a reverse equation seniority coupling, and it can be observed. You see that here, since I have at most 10 particles, that means I'm reaching middle shell already at 5. So this is system with 4 particles, system with 6 particles, let me to use. So this is not the only place you see the kind of seniority coupling in many different areas. They can be all from the same picture. Okay. There is a nice overview published by this group. I just pick up some example in that paper. So this is the isotopes, the 10+ isomer, which you get from the coupling of neutrons in each level. And so this is what you get from the protons in equals 82 isotopes, and they couple in exactly the same way. And this is some other examples. In 126, it's just saw, and sorry, this is just saw, and particularly it's quite remarkable to see this too, because you never expect each half to be isolated. There's always a mixture based on the S1 half and D3, sometimes even the D5 half. Okay. But still, if you look at the spectrum and the transitions, you preserve coupling with the shell. So I compare this with this slogan here, the Lake Michigan sink interstellar function. You can have the Lake Michigan can have a Pacific Ocean, which is huge. But meanwhile, what you see, you normally the tail. So I have a huge system with many particles. The systems can be spread around here. But what is relevant for the spectroscopy is just the two particles. In essence, it's more like a quasi particle. Many particles say. Okay. Yeah, so this is this can be very nicely reproduced. Let's do standard Chong calculations. It's a bit heavy, but doable. This is also can be reproduced, not by me. I have some problem with my connection, but I saw that there were papers that can reproduce it very nicely. I recently also got some results from the University of Stockholm. They are measuring the E plus 82 isotones, 83 and 84 isotones. They all follow very similar. That means that this is very far away from that symmetry symmetry is preserved. That is quite useful to skill. A little bit off the track. I like seniority especially because especially used with the exact solution of error hand. If you miss this daily, we know that this is good. Sometimes you get benchmark with exact solution. There are different possibilities. If you have a constant parent and the recharge model, if you have general apparent Hamiltonian, it's better to go with stack composition. I like the integration example for the T-mass top data like the image. And if you want to do a Sherman conclusions with these seven orbitals, that they want to do, dimension goes to 10 to 13. This is very, very well beyond the limit that we can do. Not reachable in any score computing. But if you train yourself to seniority there, only 100. And this is the dominant terms. That's why quite often, even if you are interested in section pattern, use this solution as a starting shell. Very far away. Okay. And I also think comparison that just maximum you can do. I always do this as a Christmas gift when computer is free. So I can add another system with 38 pairs, 38 orbitals with 19 pairs. So the dimension is 3 times 10 to 10. It's basically the limit. And if you look at Sherman dimension, it's 10 to 30, which is not trustable. No, but this is too much of the and also, if you are limited to two particles, you get the pair. Please always do this. This class exercise. Okay, okay. And this is exactly the same as the pair. And something that's less well known, but actually is very similar to BCS and to the single part state. And turns out that if you have a general system, beyond the single shell, you get the solution with parent. Can be in this way, it can be complex solution. But it turns out that if the binding energy from the system follow a very simple pattern, and like this, number of pairs times number of pairs minus 1 times the constant minus the blocking effect, which is 0 if you only start even, and plus the number of pairs times the input energy. This is exactly the same form as the single J shell. Okay, so the nature is quite simple. And this term simply comes from the blocking. This is I call the polyblocking. This is you have the ordered particle. Not necessarily polyblocking. This is an ordered particle occupying one orbital which is not available for the pairing condition. This I call the polyblocking because if you have more pairs, they have less room to develop. That means you have more pairs to a system, that it gain less. And if you just have bosons, you end up with it. So it's something that could be compared with this. Okay. And so I showed you several examples now on the possible applications in energy in different systems, in a single jet system and on a complex system. I also told you that energy is only preserve the shells with these smaller than 7 smaller than 7. But you see that in the other shells like 0.5, 11.5, in some cases 13.5, it's not still looks quite okay. That is because even for those shells, only one condition for detection preserves seniority. But here I just this will not be easy. So here is way 2, way 4, way 6, way 8, just the two-body matrix element that you do deal with in the shell model. These are the matrix element with certain spin. So here I have the two-body matrix element, coupling to a spin 2. Okay. So this is the number. And if you have the spin 2, spin 4, spin 6, spin 8, satisfy this condition, then your symmetry will be preserved. Okay, so this is the conserved interaction. But of course, in general, if you start from 4 rotation general, symmetry is broken. But this also makes the breaking point is rather small. So this conditions is really good. That's the reason why this meter can still be used to some extent. And even if you have shells with higher energy, it's similar to me. Yes.
But there's some directions that is strength.
And not in general, we always fine-tune it in mind.
Does it the delta
Delta, yes. Yes, yeah, for sure.
Delta.
Yeah, yes, that's for sure. Normally, it was just simple adjust one and show yeah. So when I was looking for, I started to be interested in this system since I was looking for signatures where symmetry is severely broken. So as we said, not broken because shells below 7.5. So I started looking at other shells. That is starting point. For example, the 9.5, which were not that easy. But you have the systems that can be reachable. For example, the neutron-rich isotopes just about 68 and below 70. So this part is reachable at the level. And all the average isotopes below T, which is very speaking easy to study. And you can also try to think about the T isotopes just about 182 jet closure, or the net isotope just about 208. So this is something that you can think of to play with. Also, I was looking into the possible symmetry breaking. That was the idea. But it tends on to like some stage they don't follow the order. So this is I showed you before my ground state for 9.5 system. Here I have 4 proton holes in T9.5. Here I have 4 protons in T9.5. As you saw before, that this ground state is 2 state, like some 2 state, and this will be other state, which I'm not classifying for. I can have symmetry for 10 plus and 12 plus, as I showed you earlier. That can also has symmetry for states for the spins. For example, here, as I took this table from this 2022 paper, I can have a 2 state with symmetry 4, speed 4, 2 state with symmetry 4, and speed. If you take a rhythm detection, this will not be the so we get a 4 plus. We study about the last 4 plus 6 plus 6 plus because we there. There has been an effort looking for this stage. This is what I just got this morning. It is still not correct. And there's this is the raster band, raster stage. And this is one possibility of possibility we can show yet. Could be a false propaganda. And there was an early paper trying to search for this stage, 6+ stage, but I think yeah, it's not very conclusive. So we don't know. But theoretically it is there. And so this is a 2-stage that could be feasible, but you may wonder why we do that. Is that really interesting? It is also that it can be interesting. It's due to the fact that not many years ago, there was 2 papers. They come from almost the symmetry group. They noticed that event calculations, they are 2-stage, both with only 4. They are pure, they are significantly observed, that can be actually used. So this is a system where symmetry is supposed to be working. Okay, just thinking about geometry. But it turns out that these 2 don't follow. We are just stay there, whatever we actually do. We are just as a joke, I just call it ghost state.
Would you go back 2 slides?
Yeah.
I just have to comment that that seniority 4.
Yeah.
There's a very strong image from that 4 to 2.
Yes, yes, yeah.
Yes. And there is a situation in which that seniority 4 comes below the seniority 2.
That could be the case, yeah. Yeah.
That's it.
Yeah, I should that could be the case.
That's it. Something.
Yes, yes, yeah.
It's a curious thing. You have to have special conditions for that to happen.
Yes, yes.
And the condition is that the 2+ has to be high enough relative to the scheme. If you lower the 2+ energy, you lower the seniority 4 states.
Yeah,
and I think that's the origin of some sort of collectivity.
Yeah, that could be one way.
That's just a comment.
Yeah. I will come back with more. Yeah, so that is one possibility. So here I have a seniority 4, here I have seniority 2, but they can change order or the order or linear mix at some point. But to start with, this seniority 4 stage does not mix, just stay there. Okay. This is, like I said, this is the arguing value to any interaction. It's preserved, state is just preserved. So whatever interaction, culture, or accumulate, energy can change. We don't have that much. This is just unique to the space there. So I was just joking that it's some kind of ghost state. So whatever Hamiltonian is good, just we can get this energy just like this. We set just the matrix element. If you change this matrix element, then it will change. So these are the stage we call it the partial symmetry conserved state. These are the 2 states. We have 2. Both with symmetry 4. So one has been 4, one has been 6. And hopefully they are here. Hopefully these are the 2. So we can go to normal interaction is roughly basically as I said, I don't say we can ignore the story, but they're roughly there. And this is obviously looking for transition properties, but just to start with, that's bear in mind that we can have these 2 stages somewhere in the system. Okay. This was found back then in numerical populations. Over the years, we have been trying to prove that theoretically. It turns out that to this analytic solution, it turns out that this 2 stage has a very large overlap with the stage that you just construct by the coupling with 2 pairs with spin 2. So I have 1 pair spin 2, 1 pair spin 2, a couple spin 4. So overlap is 0.998222, so super large, not 1. Also for the 6 plus is a coupling of spin 2 and spin 4. Overlap 0.9977. Still is not one. I don't have this also has bothered me all the time. So I don't have a unique generator for those stage. But we are roughly, there. We know the structure. It's very close to this configuration. Yeah. And with the energy-wise, we are roughly there. Okay. So this is a situation functions. This we function. And nowadays we can do an analytical solution. But we can show that is indeed we are exactly tested. Also, they are exactly preserved. Since a non-data measurement is exactly cancelled as well. At that time of doing this by hand, later on we come up with the symbolic conclusion, the symbolic channel dominance method, which you may be able to do. But later I can get analytic positive functions of different state and for different systems. And here I did actually create this very similar to what you do in standard method expansion. I start with my M scale, and then I do the projection, symbolic, in mathematical equally, then I can get my state line with a lot of range. The problem here is that I don't have the seniority preserved in the M scale. So we do is that after we get this projection, we reach state of that it is eigenvalue in a very control. With such that I know what is. Okay. And with this, you can get analytic solution for every state you addressed it. Did it for system all the way up to 21 half. That's all up to 21 half. And it is also like those 2 states I showed. These are the only 2. This is the only situation where seniority can be preserved even in a system. There's no such case as far as I can see. Our systems. Kind of pity that this is so rare, but as a school system, we can already imagine the spread quite around in nuclear charge. So usually equal isotopes, as mentioned, there's increased isotopes on lead and tin. There's enough room to play around. So that's very different. So this is the energy of the state, and then we have also wave function of the state. Yeah, maybe I just mention another 2 papers. This was one published by Newport last year. It was on the same situation. He was one who developed a simple generator of the state. What he was doing, what he found out was that if we start with the M scale, this is an M scale. Which is a mixed M scheme because it contains many. Actually, this is a ground state, it's known as 0 state. And he used this operator, which is near the number operators. Not number, but roughly number operator. And with that, it turns out that this operator spans every state except the 2 partial conservation state. So in that sense, he claimed that he got this very capital and got a generator. That generates everything else, the 2 remaining one will be a state. So it's indirect, but that's the thing is that I think the nice is that if you do this operation, it turns out it's very similar to, in some sense, to the induction operator. That's why if you start with a given state, since it's similar to induction, you can only span the state that has non-zero overlap with your original, with your starting point. Those 2 states, they have the non-zero combination with any state. That's why we never comes here. They just isolate it. Okay. So this could be an idea to go, even though it's indirect. And this is the cooperation from the Shanghai, where they start with pair as a starting point. I myself only managed to do 2 and 3. But still, you can show that analytically state is there, but you don't get, still don't get generated. It just bothered me, but not a big problem there. This is a nice paper published in 2021. The reason I mentioned this is large the existence of this state is two-stage. The reason why it's not is preserved there is actually in relation to the fact that how unique it's not just three-stage and five-stage, but it can have a different sign mixture given concentrations. Somehow related to that. In this paper, it clear that okay, this state can have plus sign, have a minus sign with no influence on whatsoever. We call it some kind of element of benefits. Okay, that makes it nice. So that, especially nice is that it's not just three. So this is exactly the middle shell. So my data state one is maybe one with a 4 point, one with 6 point, just this just integer. The nice thing is that this group does not mix with notifiers. This group we can mix, but this we can mix. I think these two phenomena is related to each other to some extent. So,
can you explain the connection very basic?
It's really proposed as analog. The things like this state, you can contribute with positive phase, negative phase equally well.
Connection is vague.
Yeah, it's a kind of vague, but yeah. Yeah, here I just show you the transition now. I brought all transition relative to 2 to 0. So 2 to 0 will be 1. And you see that 4 to 2 and 6 to 4 will be very weak, 8 to 2 will be 0, as we know from standard seniority. And here, of course, this is seniority 2. And this is a transition from seniority 4 to seniority 2. This is very strong, even stronger than 4 to 2 transition. And 6 to 4 is also strong. And this 6 to 4 is very good. This is something bad. And so it doesn't matter if you mix or not, if you are landing to tertiary stage, you need to say. Okay. There's a possibility that this state can come lower than the symmetry 2. You get just different sequence. I'm not sure yeah, I think so. So this is what you normally expect. Strong transition here. Here is a transition all the way here, since we have the same seniority. It could be a line, it could be a one possibility that this transition becomes strong. I saw this section later. Okay. I will show you the reason why. So this will not be isolated anymore, this happens. And there could be a possibility that this becomes strong, and this becomes strong, and this becomes strong. Maybe observe like collective band, even though it has different nature. So that is one, it's indeed one possibility. I don't want that to be measurable, but it could be one possibility if you have such a system. So that was one thing that I'm playing with. And trying to see what happened here, why it can be strong or why sometimes it can be cancelled. So this you can easily see, especially here, since my 8+, my 6+, they can mix seniority, but I do have one state that I will mix in. So I have 2 8+, have 2 6+, 2 components. So you can see that okay, I mix it up this. I have my state, which is a mixture of seniority 2 and seniority 4, or it's bit 2 here. You would expect that this to be dominant, and this to be small, normally, but then things can be different. Okay. And if you get to the transition strengths, this equals the contribution from the seniority 2 to 2, as you will see from here, and the seniority 4 to 2, as you will see from here to the 6. Quite far away, but it's kind of one component. And then from 4 to 4, this will be now very small. Since beta 4 and beta 4, 6, this is negligible. This will be the dominant component, and these two has the same sign. If there's any cancellation happens, cancellation, this group, it turns out to be indeed the case. If I just play a game, doing symbolic calculation, by varying the strings of one metric element, you can take any one. Usually, it's a sum contribution. You see that if my symmetry is conserved, I get this strings. If I enhance my inflection, this contribution starts with a positive, which means a negative contribution to my transition. eventually can cancel. And if you go the other way around, this can be very much lost. So that's why, due to the isolation of this stage, there are two state mix in such a way that you may be able to observe stressed iceberg, or you may be able to observe very much enhanced transition. So as for this particular H plus state, they are not as simple as they used to be. As we were looking for, they can be very different things. So you will come to like this, or you will come to this calculation and this measurement.
So if you go back one slide,
yeah,
there's an issue here is contact is very close.
Yes, yeah. Yes.
So the number of particles G9 has is not well defined.
No.
And that's a problem.
That could be a problem. Yes, yeah. I played. Yes, here it comes. Yeah, I was playing with the model space. As you see, you see that here the result more or less the same. Here more or less the same. I think different here. Let me print out. The thing was like you, as I said, you will never get back to how to be very it's always a mixture. Okay. For things like even if you have a mixture and the DRAM half long shells, that's most mixture come from parallel connection. You have two particles of representations of this. But in the spectrum, they are more dominated by the company using single particle building. The most configuration usually are not anymore. They still dominate of this precision. That's why even though this configuration is 4 particles in the up, they become less dominant. 60%. That's the component that you generate transition. This is what I mean. The P1 part and the part of the P3 complete more through parallel connection. It's scattering pairs across the computers. And here, it has come from that into more orbitals. This mixture modifies the mixture within the shadow. Yes, this is concerns the seniority isomer. Then, of course, since I have done that, I will start playing games at other stage. So I was going to see. Okay, so I start to look at the 4 plus into 2 plus. I played it's quite common to do the numerical environment and the shallow calculations for many different actions and many different model spaces. It turns out that in some cases, generally, is what we get. They are quite small. In some cases, this is those tremendously enhanced by more than a factor of 10. This happens in some model space, happens in actions, but not always. I did not find a universal feature yet. At that time, so okay, let's start looking into that what happened. If that's really a consultation into the component development.
Is experiment with this?
Yes, not here. I will show you something that coming. First of all, I just want to show this is an illustration of like why, if I have many more shells, my unit is actually broken. So this is my situation. Start with, I have one unique defined state, and all the non-diagonal elements be 0. That's why it never mix. But if you expand your model space, even though these are still 0, this element, we interfere such a way that you get a small mixture among yourself. This could happen. This is the reason why we will impact some mixture we have a larger model space. But the same selection, this one is the dominant. This was illustration of the application in reality, but this is more in the channel. Okay. So this is what happens. Okay. So I play games with starting with a single layer shell, and then I include other shells, do it 1 by 1 or several by several. This is one combination of the including the and the B1 up, and then I adjust the non-mathematical section. These are one of the I promise you that I've done questions in dynamic model space with functions somehow, which we will see. Okay, so I will start with my data hub here, where I have the scenario 2 scenario 4 stage, which we didn't mix at the beginning if you don't have the other shells. And you see that at some point, it's quite universal. At some point, you have a something flip between the two contributions. This goes down quickly, this goes up quickly. I usually say, okay, this is just the flip which just happened. So I can have these two just change order much. The same is like you see that here, we're not going to flip. These two states they can cancel each other, leading to a nearly zero transition, which you cannot say if it has done this. Okay, so here we number 110 here come to 0. And here we have a dramatic enhancement. Since the enhancement is not less significant, you will not be after this level measurable. But this could be a smooth evidence for existence of this kind of. Okay. So this was my argument. But of course, I'm going to tell you that okay, this will never be measured. If you do an environment, it will be scattered around in one state here, this state here, you never know what happens. The life can be simple. Since we might go to Russia. I'm looking into this environment. It was down actually, I think that it was around 2002. People published 2017. You see what the transition. 96, the 42 transition is only 3. Here is larger than 56. Then there's this dramatic difference. They are claiming that this one responds to this function. This one will respond to this function. But if I have symmetry conserved, these two will be exactly the same, just negative. It should be follow the conjugate, the symmetry, but no, they are. This is simply use the fact that we are here. Okay. And then you may wonder why the different action gives a different result. It's simply due to the fact that it's okay. But due to the fact that here we have a unique situation where normally if you do perturbation theory, you have the first dominant by the leading component and the non-dimensional elements here to contribute finally. But here, all the leading order terms cancel each other. The only non-zero element. That's why cohesion is so sensitive to that. If you just start with any polynomial, you will see that this appears in a very small window of your experience for the non-dimensional. Okay. That's why we normally don't know. It's very difficult to find if I need to. So quite often you really end up here or end up here. But fortunately, nature tells us that we should be. This was one environment. And of course, people have different opinions. In that paper, they stated that it has replaced the feature by including the cross-check substitution. But as I was showing you that this cross-section association does not contribute in a way that we benefit, but in a way that just makes my symbol false in the stage. So I think this calculation agrees with this. So this was unsure. We only know the lower limit. Unfortunately, I was in a group and council to do another experiment. So this was the first experiment at fair 0. I suppose just the normal TSI with the dispatch setup was people can launch last year. This is the data we got. So this is 103. So that it's 30 times larger than the 94 position. That's an indication of indeed one nuclear scale distance scale. Okay. So this is from my perspective, this is clear evidence of the existence of the state. There was a follow-up paper, but it's good. Done at the TS setup. We got a lower transition for this, but it's not significantly lower, so I don't mind. So really, I think that people do it is here or it's here. It gives us a conclusion. to have state. Of course, you don't want to move this. So this is one environment. This is an environment that will hang around for quite some years now. It's published about the level 72 and 74. I think here is similar. And here you have the normal sequence with nearly 0.2 transition. Here you have the peaks where you have this enhanced 0.2 transition. And the theory gives you very enhanced, but I do not worry about that, just as I said. This is simply due to the fact that I have this transition-like behavior. By chance, you can be here, you can be here. Why the T can't decrease in the non-mathematical element, which is big thing. Okay. So this is one. Maybe I should end up. So we are trying to analyze the function in more detail now, since I'm going from my shelf. I saw this very nice paper published last year on the entanglement, but on the entropy, which gives you the density matrix of the state. You can issue the mixed scenario 2 and 4 gives the result in nearly the same as the shell model. So I think this is an indication that this kind of simple picture follows the complex equations that I had to recommend. Maybe I should conclude. So hope I delivered information like seniority can still be conserved in some cases about 7.5 shell. In particular for my z equals 9.5 orbital, which you can see in the 70 cases. This kind of seniority conservation feature is measurable now. Not only is neutral deficient, but also neutral rich. It is measurable. Europe is measurable for sure. Actually, I say there was one environment proposed that not pre-FU at MSU. There was some problem with target. There's still some topic with Rahi that I think this is still doable. We are quite happy with this simple problem that explain complex data. There I can select this kind of different level of observing between 94, 96, and 72, and 94. They are evidence for the concept of this kind of seniority. Of course, people have different opinions. This is a simple picture. And we don't have a very simple picture of the function yet. So I don't have a good generation of the function. But I think this will come. And I don't have Hamilton that you produce everything at the same time. Since the universe tools and the incorrect tools are so different. Since the code are so sensitive to the non-linear measures element, which is not easy for me to do. If the fun part, since you focus on you can help to advance and that case you can really do a very good way to test the shell model and in general. There will be one more event to follow, but hopefully it will clean up everything. Yeah. Sorry for the long assembly of that.
So about this, the symmetries work away from the magic and magic.
If you are far away from the equal Z, it works still pretty well. But the Levi code, if you add more plot, to be fine. But for the receiving and grading, that's tricky. If you add one more plot, it's like everything. We will that's one very be done next week. Same thing. Just add one more plot like that.
First, you mentioned amyloids. Can you explain a little bit more about that? So you want amyloid to help finding a proper.
I was thinking about the optimization coming from there. Normally, you do optimize one way attention, which is relatively easy, just with the programs or the long-line state. Here, it's tricky because so many non-mathematical which may not be sensitive to any observers. I was thinking as well to do as many equations as possible to very conservative if you can have a good starting point with one wave function as an parameter. Maybe we can change one into a certain that can span larger model space. And when you think it would be the parent system.
But that requires your animation to
Has to be
not just
rather-
browsing, but also effects.
Yeah, that I can do, and one has to be accurate enough from the phone.
Okay, if you don't have more questions, thanks, speaker again. Yeah, so just remind you, on Thursday, we're going to have a coffee discussion for the seminar next week. That's the first thing. The other thing is that leaders have set up a speaker, so anyone who want to join, let them know. So then we have fixed schedule.